PSF as a whole from images which I will show that usually have aliasing. Since they have aliasing, I can do subpixel estimation of the PSF. So I can resolve the PSF at a resolution which is below the pixel size. So the motivation for that, I think it's already clear from the previous talk. We have blur in images which is caused by wrongly setting the camera focus, for example. This I won't take it into account. Because the scene has different objects at different depths, so we won't consider that too. We will assume that we are looking at a fixed plane. You can have camera shake, you can have scene motion, all this I won't consider it because I consider to be extreme. I consider them to be extrinsic sources of blur. So this is the blur I'm interested in, which is the blur which is due to the camera, which is due to diffraction, the sensor averaging, lens aberrations, the optical anti-aliasing filter that every optical system has. These are the kind of things that I'm going to model all together in a kind of black box approach. So the goal, as I said, is to accurately estimate the point spread function, which is the blur due to intrinsic camera phenomena. This is the area pattern, the response you have because of diffraction, but the PSFs in general look similar to this. So the dominant term here is diffraction. But there are many problems in image processing that would beneficiate from this estimation of the PSF, from knowing precisely the PSF. One of them is image zooming or super resolution. Anti-aliasing. If you want to do super resolution, you need to have a super resolved PSF estimation. Otherwise, it's not true super resolution. So super resolution with one single image or with multiple images. And this is the most simple application, but it's still very, very important, which is how to assess the quality of an optical system. Usually camera manufacturers or lens manufacturers give charts of the lenses, and what they give is something, a representation, a different representation of the MTF, which is called modulation transfer function, which is the Fourier transform of the PSF. There are two ways to face this problem. The first one, which is the hardest one, is blind estimation. It means that you take pictures of something that you don't know what it is, that you don't know it precisely. Maybe you know some statistical properties. For example, that you are taking pictures of a texture, or that you're taking pictures of a scene that contains edges. An edge can give you information about convolution with the kernel. So there, if you know that an image has edges, then you can retrieve the PSF. This is not quite really true, because most edges in images happen because of occlusion. So it means that when you see an edge, one part of so to the one side of the edge, the object is at a given depth, and to the other side it's a different depth. So the convolution model there doesn't work very well. The steps are useful if there are steps on the plane, which means it's just something which is paint on a wall, for example. So blind estimation techniques assume that, for example, there are edges in images, or that the images that you are acquiring have some random properties that are known in a statistical sense, etc. Then you have non-blind estimation techniques, where basically what you do is taking a picture of a target, a calibration pattern, that you know it very precisely. You have also other kinds of approach. You can also make different distinctions, for example, between parametric and non-parametric. Usually, typical parametric approach would be, I assume the PSF has I don't know, Gaussian shape, and then I try to fit parameters of this Gaussian. The approach I'm going to present here is a non-parametric approach. It is non-blind. I'm going to take a picture of this target, and it can deal with aliasing. Okay? So it can give subpixel PSF estimation. This is the target we use, and I'm going to give I'm going to explain why we use this target later at the end. These are targets that are used. These kind of targets by people who do PSF estimation. Then this is like a state-of-the-art work in PSF estimation. Propose this target. So you see, you have edges, and the idea here is having edges at many directions. If you have edges just an edge like this, then you could only estimate the PSF in this direction. If you have edges at all the directions, then you can estimate the PSF in all the directions. Okay? I'm going to show that this is better than this. So I'm going to summarize the image formation model I use now. I have an image U, which I assume to be planar. I'm controlling that situation. I'm taking a snapshot of the plane, the target, planar target. This undergoes distortion. This distortion is basically homography. That's why I talk about homographies. It's a transformation from a plane to a plane, and some geometric distortions due to the lens. And I can model all that together here in this D. This gets convolved by the PSF. This is the guy I want to estimate. G is the nonlinear response of the captors. If it was linear, then I could forget it. But it's not linear, but it's quite linear. Okay? But we're gonna take that into account too. And then this is the sampling operator of rate 1. Then I get the image V, which is a matrix. Okay, these are samples, because all this continuous image is sampled in a regular grid at rate 1. That's why this is S1. And this N models noise. I'm going to talk about that later. So here you can see the chain that brings this model. You have first the projection, then the lens distortion, then you have aperture that gives diffraction, aberration, out of focus, etc. Then you have an optical low-pass filtering, then you have integration in the sensor, and then you have your image, your discrete image. So we assume that H, now we're gonna, so now the problem is not, so we know U is given, is my target, and I want to estimate H. So you see I'm not taking any prior assumption of the shape that H should have. H, the PSF, we assume that it is band limited within this support. And if we take samples, if we could take samples of H, at least at delta rate, then H would sample according to the Shannon-Whittaker theorem, And you can show this equality which relates discrete images with continuous images. This is the Shannon interpolator. Okay? It's the same interpolator. Parameter level. So then, this continuous convolution, I can replace it with this. So now, everything I have here are samples. H is my PSF these are samples of my PSF, but it's well sampled, so once I will get H, the samples, I can retrieve H. And the UD here is the distorted image of the target, my observation, and where I cut off the frequencies which are above delta, and then I sample it in a delta grid. So this is my discrete mode. I'm going to work with this. So this would be linear if it wasn't because of G. So it amounts, finding H amounts to solve this minimization. Here I'm assuming that, and implicitly when I do this, I'm assuming that the noise is Gaussian. That's why this makes sense. Okay? That's why minimizing the this is an Eltron norm. Makes sense. A very important comment here is that H doesn't need to be, and it's not actually space invariant. So it's not a convolution, actually. I write it here as a convolution in a local sense. So locally, I can approximate the H as a convolution. But then when I switch from one point of the image to another, I will have a different H. So the H here, the shape of H, changed with position in the image. This is because of lenses, of many things. So H, we will consider that H is spatially variant. We will solve for a small piece of image that will give us an H, and then if we want H at a different location of an image, we have to show the pattern as at a different location and take another picture and do another calibration, and we get a different H. But we assume that this H varies smoothly. Here I'm going to concentrate on estimating H on a given image location. So as I said, this is the target we use. This target here is white noise with Bernoulli distribution, 1/2. So 1/2 probability of being white, 1/2 of being black. And these points here, these patterns here, I use to compute the homography. Remember, I need 4 points to compute the homography. Well, here I have more than 4 points, so I could compute the homography. This is a possibility, but then homography won't be enough because there are distortions due to the lens. So we have to see how to estimate the distortion term, which is lens distortion combined with homography. So we take a picture of a given location. So we put the target somewhere and we take a picture, and the place where we take the picture is going to give me the location of the H I will estimate. So the algorithm is very simple. We capture an image. We detect features, which are the ones which are in the border. With that, we can estimate illumination, because these features here there's equal area of white and black, especially here too, because this is 1/2 probability of being black or white. So I can do illumination estimation. I can estimate the geometric transformation that maps my target, my real target, to the observed target. using the points I have put on this pattern that circles the noise. That on one side. Then I have to apply the geometric transformation to the original target, which is a rasterized image. It's an image that I know very well. So if I want to do S times super resolution, I can rasterize the image. So I make an image which has a resolution higher than that. With that, so with the illumination correction here, I can do normalization of illumination in the image. I can correct the contrast. And once I correct the contrast for being linear, I can forget the nonlinear capture term. And all that together gives me the PSF estimation. Basically, it's comparing two images and putting them into the image formation model I talked to you about. So how do we do feature detection? These features, which are here. Well, I need to detect corners, and there are checkerboard corner detectors in computer vision, which are called, one of them is called Harris-Steffens corner detection, and it gives subpixel accuracy. I need subpixel accuracy if I want to use subpixel PSF estimation. And as for the geometric transformation, the model I use, so once I have identified the features, I have to map the features in the image with the features in my ideal target. So I can fit a model which will be a thin plate spline model, and that will prove to be enough because I'm working in very small patches. If you look at an image, what the typical size of the pattern has in the image, which is this, is very small. So splines are good enough to approximate the transform that maps the pattern here to my ideal pattern. So I detect the corners in the observed image, and then I define the correspondences with the points in the ideal target and compute the thin plate splines, and I get the geometric transformation. So one thing you can notice here is that I don't need to separate the homographic distortion from the non-homographic one. And that is something that typically has to be done for computer vision tasks, because I need to know the geometry. So typically the non-homographic distortion would be the lens distortion, and I have to correct it, and then I have to separate the two transformers if I want to do 3D, for example. Here I don't care. I treat everything together. Homography and lens distortion and any kind of geometric distortion. How do we estimate the contrast function, which I said that it was linear? Since I know the target has half black and half white squares, I know that the ideal mean should be 0. So what I do is correcting the image. So I estimate G by correcting the image to have 0 mean value, and I take as G a second order polynomial, and that's enough. So in that way I can estimate G, the nonlinear response of the CCDs, and in practice I would say that I could consider that G is linear without having any problem. It's very, very close. Actually, these responses are very close to linear if I work outside the saturation zone. I'm in the saturation zone. I have one here. Above some level of light, you have white saturation, and below you have black saturation. If you are outside these bounds, inside the region where you normally take pictures, non-saturated pictures, then the the response of the CCDs is very close to be linear. So in that way, the last thing I explained is this, how to correct I'm not getting into the details because I won't have time. But you can look at, I give references where you can see where each step, how each step is performed. Okay? So this is for the contrast function, contrast function correction. This is for the geometric correction. And then I can do the PSF numerical estimation. And the way to do it is very simple. You have to solve for this linear problem, this least squares problem, and you solve for H. This matrix U here is a convolution matrix. I can write, convolution is a linear operation, so I can write it in matrix form. And that would be a convolution matrix. The convolution matrix U depends on the target. So it depends on the kind of target I choose. If I choose a noise target, U will have some kind of shape, and if I use the other target I showed to you, the one which has like black and white waves, something like that, then U would be different. But in any case, I can find U. V is the observation, and S is the S downsampling operator. And I have this constraint here, which imposes that the PSF is positive, which is something we know. You can solve this in many ways, and you can do it quite fast. So, yeah, a good test to see if the modeling is good is trying to eliminate this constraint and see what it gives. If my modeling was good, or at least I know if it's, I know the contrary, I know that if my model is not good, then when solving this problem here, I can get an H which is negative. Okay? So, another version we have is solving this problem without the constraint and see if the solution we get is positive. If it's positive, we have a hint that our modeling is good. So you have to, basically you have to find the pseudo inverse of this matrix here, SA, SS, U. This is the Moore-Penrose pseudo inverse, and you get the estimate of H. How good would be my estimation? It depends then on the condition number of this matrix. If the condition number is good, then the estimation is accurate. So now what we want to do is to give a measure of how accurate is our estimation. So we need to estimate the error of the estimation. You can see from here that the estimation error is the result of applying the pseudo-inverse of our matrix to the noise. I have a model for this noise, which is white Gaussian noise, of standard deviation, this value here. Actually, the value it has is not important. My assumption here is that the noise is white and Gaussian, which for a small patch is a good enough model. So in that case, the estimator HE is unbiased, and the variance of the estimation is the power of the estimation noise. which is given by the Frobenius norm of the matrix I want to invert. What is the Frobenius norm? The Frobenius norm is this, is the sum of the inverse of the singular values of the matrix. That's why if I have zero zero singular values, then the Frobenius norm is infinity and my accuracy, my error in the estimation is infinity too. Okay? You can't invert a system that has a zero eigenvalue. That's what's happening here. If all the singular values are non-zero and are pretty high, then this value here that I call gamma, which is a number associated to the matrix I want to invert, would be large enough and I could invert the problem very well, and I would have a good accuracy in the estimation. Okay? So our goal is to design. So look what we are going to do now. We have the freedom to design U as we want in order to minimize this. Okay? Because if I minimize this, I'm minimizing the estimation error here. This is my goal. So I define an optimal pattern to be the pattern that gives me the minimum gamma SSU. My goal now is to find bounds on this and then trying to find real patterns that get close to the bound, the lower bound of this function here. You can forget about this. So we have a lower bound which is not asymptotic. This is important because my pattern is small. I can't make the pattern large. If I make the pattern large, then they have a problem with the locality. I told you that the convolution kernel changes with location. So I have to have patches which are targets which are seen in the images in a small enough size. So if the size is large, I will be mixing things that change in space. If the size is very small, I will have more noise. So I have a trade-off there. But the pattern has to be finite, so I need an asymptotic bound for this. And we have an asymptotic bound that will enable us to design calibration targets. What we're going to do is we're going to try with different targets. We're going to find the one that get closest to the bound. So here I'm showing in red this lower bound for the error, for the gamma function. And this is for a kernel with fixed support R and different sizes of the image patch of the target I'm using. Okay? This is how it evolves. Here I'm fixing the size of the image of the target, but I'm changing the support. This is the only parameter I have, the support of H, which is the number of samples I have of H. So here I fix the size of the target in the captured image, and I change the size of H, and I see how it changes. So here, what's important to see is that when you use the target we use, which is white Bernoulli noise, a realization of that noise, we get the blue line, and you see that it's really close to the red line. So it means that we are close enough to the lower bound of the error, and in practice we can consider that this pattern is optimal. So the error is so small that we can consider that this pattern is optimal for the PSF estimation problem.
Pablo, what is the axis there?
The axis here is 0, well.
No, but what is the magnitude?
Yeah, here it goes up to 0.8. But what does 0.8 mean?
Right.
I will show you that later. I forgot to put this there. Okay?
But the theoretical bound is the CR parameter bound?
The bound?
Yes.
No, it's a bound we derive with the Kuhn-Tucker condition and this kind of convex analysis. But this is a non-asymptotic bound. This is for an image of size. So I take the picture of the target, and the size of the target in my image has m by n pixels. And this is m. And the size of the kernel, I'm assuming, the support of the kernel, is that the kernel is an R by R patch, and this is n. So this gives me the bound. So for practical purposes, this noise target is optimal. Now I'm going to compare the eigenvalues we have for when using our pattern and when using the other pattern I just showed. Okay? In blue, these are the eigenvalues of the noise target. In red, the eigenvalues of the Joshi pattern. So you see that, and they are ordered in decreasing order. So if you take the inverse of these things, this explodes, and it gets far from it gives a very high gamma value. You can see it here. Okay, so the bound for a 9 by 9 kernel, PSF kernel, would be 0.1. Our target, the gamma value gives 0.19. And this is 100, and the difference gets larger as the PSF support gets larger. Okay? So obviously, in a situation like this, when using this kind of target that gives these eigenvalues, you need to regularize the solution. What does it mean to regularize an inverse problem? In a least square sense, when you have to invert a matrix, you have to perturb the matrix by something. For example, adding some epsilon times an identity matrix. Okay? But you are regularizing, so you don't know what you get. So you can you can avoid this problem just by using a noise target. Then you will have an exact estimation of H, which doesn't assume anything. Because when you regularize, you are assuming some kind of smoothness on the solution, etc. So this is a comparison with a synthetic example. So with a synthetic PSF. This is the true PSF. It's a synthetic one. I have built it. And this is the estimation we get with the Joshi algorithm, where there's a parameter here, which is the amount of regularization. When no regularization is used, this is what I get, and this is the difference between this and this. This is brought to the same size as this. This is subpixel estimation, so this size, the size of the estimated is larger. So, no, sorry, forget what I said. You take the difference between this and this, scale, and you get this. This is the image of the difference. You want that to be gray, the most uniform as possible. If you use a medium regularization and you take the difference, then it gets a little bit better. If you take a high regularization, it gets a little bit better, but it's not good enough. And this is what we get in our approach. So you can see the signal to noise ratios here, and this is an image of stability. we repeat the experiments many times, adding random noise. So we see what the curves are, we plot them all together. So this is what we get. We don't have any regularization parameter. Now experiments with real cameras. We take a Canon camera with a Canon lens, and we take ISO 150 millimeters for the focal length, and we observe the green channel. And our goal here is to do 4 times PSF estimation. So this is the PSF we get. This is at the center of the camera. I have to define where I'm estimating the PSF, okay? For an aperture of 3.2, this is my PSF. For an aperture of 32, this is my PSF. So you see it gets larger, okay? This is normal. This is the MTF. This is the Fourier transform, the modulus of the Fourier transform of the PSF. The same. So you see the opposite. Obviously, if it's more concentrated in space, it's less concentrated in the Fourier domain. Okay. This is just a different representation. Here I'm showing profiles of the MTF in vertical and horizontal directions for different apertures. The same experiment, it's a different plot. But here you can see, so here 0.5 is the Nyquist rate. So when I'm here at 1, it means that I'm doing a half pixel precision estimation. Okay. So I'm estimating here at 1 at twice the Nyquist rate. It goes up to 2 because I'm doing 4 times super resolution. So you see it's pretty smooth, and it starts having a little bit of ringing when I go to the higher frequencies. Well, this is again the target and the zone I'm imaging. Here is 110 pixels by 110 pixels. This is a test for stability with a real camera. I take many pictures. I estimate the PSF. So the location is fixed. And I take many pictures. I do and I plot them all together, the results. Here I'm showing the average and the average plus minus the standard deviation. The resolution in the screen is very bad, but you can see that the stability is very good. Another experiment which is looking at what happens at different channels. Before going to that, look at this is typically CCD or capture. It has the 3 colors here. And then so in digital cameras, then there's a stage which is called democycling, because the color image is captured on the same array, but then you have to separate the channels, and this is called democycling. So this is called the Bayer pattern, and there are twice number of sensors for green than for red and for blue. So this is called the R channel, the blue channel, and the G1 and G2 channels. So for the red channel, this is the PSF I get. For the blue, this one, green this one. So green channel 1, green channel 2. For a 4 times PSF estimation. These are the MPFs of the estimations, and there's something you can see is the fact that you have these directions here, okay, which seem rotated. Well, these rotations are compatible with this with the active area of each sensor. These sensors are called L-shaped sensors. So it's natural to get this kind of behavior where you have the green in these directions, and then the blue in this one, and the red, well, the red more. Okay? They are rotated 90 degrees. This is a nice confirmation. Different locations. I take the picture of the target here, here, and here. Well, then you see that at the center I have something which is pretty symmetric, and then at the borders, mainly because of the lenses, I have things which are not round. Finally, this is a comparison with other methods. I know it's very hard to see from there, but ours is the random target is the one that goes here. The one that is like noisy, which goes up to 1, is a commercial software to do PSF estimation. It goes up to twice the Nyquist rate, so you can do up to 2 super resolution, to 2 times super resolution, and the rest of the curves are the Joshi method by varying the regularization parameters. So you see that there's a lot of variation in the Joshi's method in high frequencies when you change this parameter. So this is all for the non-blind PSF estimation technique. I'm finished, almost finished. So now, what about going to a blind estimation technique? Well, we are working on that. The idea is to take 2 parallel snapshots of the same object, a planar object, and use the relationship between the 2 images to derive the convolution kernel. And this is much more tricky. It's trickier than what I've shown. The formulation is a little bit non-intuitive, but you can do it. You have to estimate what is called the inter-blur kernel between these 2 images, the same object taken from different distances, more or less frontal-parallel, more or less because I can correct for these things anyways by doing registration. There are ways to do that. So if you manage to estimate the inter-blur kernel, one can prove that you can estimate the PSF. And this is ongoing work, but I can show you some results. Well, this is an estimation that doesn't say much in this context. What is better is to see the comparison with the non-blind methods. Okay, and so the random target non-blind approach I showed to you is this blue dashed line here, and the one which has these little circles here is the two-scale, what we call two-scale method, is the blind technique. 2 snapshots of the same scene at different distances. It goes here. Okay, it's not very far from the non-blind solution, and I would say that it's maybe better than even the non-blind approaches I'm showing here. Okay? So this is the direction where we are going now. So I'm going to skip this, and I want to talk to you about this project, which is called IPOL. It's Image Processing Online. This is the web page. So this is IPOL is a project to try to avoid that people keep on cheating on image processing. Okay. So what's the way of doing that? It works like a journal. You have to submit a brief summary of your algorithm, and you have to submit the algorithm and the source code. And then there's a web page where people can upload their pictures and run exactly the code that you wrote in a paper, for example. Okay? And you have all the description there. So it has a peer review system. It's exactly like a journal, but it has this site, very nice, which you have, for example, for hours. Well, again, I can show you that later if you're interested in that, but our algorithm is there. You can upload your pictures, and then you say, you press run with the parameters you have to choose there, which are the size of the kernel and the times, the super resolution times you want to, how many super resolve you want to do your estimation, and that's it. You upload your pictures, and you press run, and you get the result. And the algorithm that runs there, which has a description and you can download the sources, is the one which is used to run the experiment. So no cheating is possible there. Okay? And you can submit like in a regular journal. So it's very interesting for people doing image processing to proceed. Thank you.
Pablo, a question. What degree of aliasing does it work? How much aliasing can you have?
Well, I can show you these pictures. I would say that 2 times is safe. 2 times the Nyquist, even 4. We cannot go farther than that. But 2 is really good.
And the performance will degrade as you increase the aliasing?
Yeah, it should. Yeah. But so my final, just a final comment. I told you that optical, very good. This is a good camera. It's a Canon camera, DSLR camera. It's not top quality, but it's a good camera. Okay. It's not just a point and shoot camera. Well, you see that normally, if it was sampled at the Nyquist rate, the PSF should vanish here. The MTF should vanish here. Okay, so it means that there's aliasing. Okay. You have frequency components above the Nyquist sampling rate.
Any more questions? Okay, so we have a lunch break now. We will come back at 2.